Okay, so I'm going to talk about simplicial categories and homotopy coherence. The first point, we will start with some motivation, how to produce quasi-categories. The answer is following. We will introduce the following junction, which consisting of two functors C and the functor R. The first one is a functor producing simplicial categories, and the other one is a homotopy. So the aim of this talk is to produce such functors and recall some basic definitions. Simplicial functors. Simplicial functor F between simplicial categories C and D consists of functors Fn for each n that commute with the simplicial operator functors. For example, consider the following simplicial functor from simplicial category C to simplicial category over simplicial sets. Then for each x, we should specify fx together with the following map for any n simplex in this simplicial set, such that the faces and the generators of this map correspond to the ones of the n simplest. That's just a basic definition. The next point is about simplicial natural transformations. So if we have two simplicial functors, they is given by arrows in the underlying category of D for each object of C. In other words, we have the following data: the set of alpha x for each x in category C. Alpha x is just this zero simplex. Okay, and alpha x form a natural transformation between f0 and g0, and we have the generators, and they should form higher natural transformations. So in general case, the images of the alpha x under the unique degeneracy operator form a natural transformation between fn and gn. So this is a definition. Okay, now introduce some natural functors. If we have a set, then we can form a simplicial set from this set by means of the constant enrichment functor. We just we consider the simplicial we can consider constant. Constant functor from this category to simplicial sets. In the target, we will have a constant simplicial set, and of course we can consider the homotopy functor from simplicial sets to set. We just take by zero, and also we can consider the underlying category functor, or just the functor for which we have which takes for any simplicial sets the set of morphisms from delta 0 to this simplicial set X. And it can be shown that these functors are monoidal. It means that they are lax monoidal and oplex monoidal, and we have an we have isomorphisms in appropriate way, and so as these functors are monoidal, so they induce the functors between the following functors between enrichments. So, for example, consider the functor C, and we can apply this functor level-wise on home spaces, and after that we will have the following guy, and so we can take a category in the category of small categories, and then we will obtain some category, some simplicial category, and on home level, we just take a constant simplicial set on each level. Okay, and in the same vein, we can apply the homotopy functor to each home space, and then we will have we can form from the simplicial category some usual small category without with a trivial enrichment in ordinary sets. Okay, and of course we have the later functor, and we just apply the functors to home objects of the corresponding categories. Okay, and these functors are important for us. Okay, okay. Now discuss weak equivalences between simplicial sets. So the definition: a simplicial functor f between simplically enriched categories is called a weak equivalence if it induces the first point is that weak equivalences on all home simplicial sets, that is it is weakly fully faithful, and the second condition that it's an essentially surjective function. So this is a condition. This is a weakly essentially surjective condition. Okay, this is a definition of a weak equivalence between simplicial enriched categories. Okay. Now, simplicial categories and simplicial objects. We can. It turns out that we can think about simplicial categories and simplicial objects in different directions. They are the same objects. I mean that any simplicial category, say C, gives rise to a simplicial object C in the category of small categories. So we can just write down these CIs, and for each category Cn has the same object as C. But what about morphisms? We say that we have a simplicial category, and then we wanna form a simplicial object. So n simplices of these simplicial objects are just n simplices of the corresponding home object. Okay, it's a very natural way to think about it. So in particular, C0 is just underlying category of C, because we just consider morphisms from delta 0 to our home objects, and of course, by definition, this is an underlying category. Okay, and conversely, if we have a simplicial object C, then we can form a simplicially enriched category, or just simplicial category. Consider the following operators from this data, and these operators are the identity on objects, and find n simplices in home object is just n simplices in the appropriate of the appropriate model of the appropriate category. Okay, so the simplicial action will be specified by the use of functors di and si, and so it means that of course we can think about simplicial categories and simplicial objects as like synonyms, or they are close to each other. Okay, so now discuss the topological and simplicial categories. What are the what's the difference between topological and simplicial categories? So the answer is there are no differences. We have an equivalent adjunction between simplicial sets and topological spaces, and it produces, of course, an adjunction between enriched categories in simplicial sets and in topological spaces. So this is by the fact that this adjunction is a monoidal adjunction. Okay, so we have the following diagram, and thus, we can think about this enrichment as just an enrichment in some homotopy types. So by definition, we can take H to be homotopization of simplicial sets, and this is the same as a homotopization of topological spaces. These notions are equivalent. Okay. And we and when we for the work, it's not important what do we use. Certainly, okay. So locally simplicial categories and Bergner's model structure. It turns out that if that on the category of simplicial categories, there is a interesting model structure, so-called Bergner model structure, and now we discuss this point. So by definition, a simplicial category is locally CAN if each of its home space is a CAN complex. There is a cofibrantly generated model structure on simplicial categories. Sorry for this. And in this model structure, we have that weak equivalences are just simplicial functors that descend to H equivalences. That we on home objects, we just take homotopy functor, and after that we should have equivalences. So fibrant objects are locally simplicial categories. That is such categories in which home spaces are CAN complexes. And what are the generating cofibrations? Generating cofibrations are the following. Denoted by 2 of A as a simplicial category with two objects, say 0 and 1, and home spaces just you have two objects 0 and 1, and there is one home from 0 to 0 and one arrow from 1 to 1, and the only one arrow between 0 and 1, and there is no arrow from 1 to 0. So okay, can consider and of course the sort of this, but I mean that this arrow corresponds to some simplicial set A. So we have this two trivial simplicial sets, simplicial set homes, and the latter is arbitrary. Okay, and theorem. There is a cofibrantly generated model structure on simplicial categories whose weak equivalences are simplicial functors between simplicial categories, such that the homotopy functor applied to this functor produces an H equivalence, and fibrant objects are the locally simplicial categories, and whose cofibrations are generated by these these functors. Okay. Okay. Now to define more fruitfully the notion of cofibrant generate morphisms, I mean that we wanna find the way more we wanna find a convenient way to work with these sets, and it turns out that generating cofibrations can be described in more convenient way by means of so-called simplicial computads. But now recall that in the simplicial category is just n simplex in the simplicial set from A to B. And by Eilenberg-Zilber lemma, any n simplex can be decomposed in the following way. Say that f equals the composition of f prime and alpha, where alpha is some epimorphism, and f prime is a non-degenerate M arrow. And in this case, we will say that f has dimension n. Okay. And now the definition: an arrow in an enriched category is atomic if it admits no non-trivial factorizations. So if we have this factorization like this, then we have no we have no then there is no an alpha or f prime, something like that. Okay. So the definition, the next definition is about freely generated categories. A category is freely generated by reflexive directed graph if each of its arrow may be uniquely expressed as a composite of atomic arrows. So if you have an arrow, so you have some directed graph, and from this directed graph, you can construct a category which is called freely generated. You just take as objects. Objects are the same, but the arrows are composites of the original ones, and thus you have some category, but also we want to have atomic arrows, and we require that any arrow may be uniquely expressed as a co-composite of atomic arrows. Any arrow. Okay, and in this case, we define a simplicial computad in the following way. We say that a simplicial category is a simplicial computad if each Cn is freely generated in a sense of and for each surjection from M to M and atomic arrow, the composite F with alpha is atomic in Cn. It looks like perhaps an ideal condition, but it's not. Anyway, so okay. So the trivial example is a discrete category. But more interesting examples we will give later. Okay. So we can simplicial computad is a simplicial object in category of small categories, and each of whose categories is freely generated on set of generating arrows that include the degenerate images of all lower dimensional generators. So you can think about this object of this guy as the following the following sequence. So on the first step, you consider all possible compositions in your graph. So any possible compositions, and in higher levels, you should put some brackets, some parentheses, and on each level you have only non-degenerate simplices in dimension well in dimensional 0 you have only non-degenerate simplices, and okay, and it turns out that the following lemma holds. The simplicial computads are the cellular cofibrant objects in simplicial categories. Furthermore, every cofibrant object is cellular and hence simplicial computad. And the proof. So we have the following convenient, the following fruitful description of the set of cellular cofibrant objects in simplicial categories. And later we will see that it makes sense, and by means of this construction we can produce a construction of coherent nerve. Okay, now the proof. So we will prove the direction, the following direction. We prove that any cofibrant simplicial category is a simplicial computad. Okay, and for doing that, we check that a retract of a simplicial computad is a simplicial computad. You know that if you have cellular cofibrant objects, it is formed by different products, co-products, pullbacks, and push-outs, and retracts. So we have some composition of these operations, and but we should only verify that a retract of simplicial computad is a simplicial computad. So consider some retract in this category, and we suppose that C is a free category, and consider retract in this free category, and we should prove that this retract is also free category. So it follows from the fact that each arrow in this free category is monic and also is epic. So if we have the following quality, then this equality, for this equality, we have some analog of 2 of 3 property, and if any 2 of these, if any 2 of these are in B, then so is the third. And by induction, any arrow in B is uniquely decomposable into the shortest composites of atomic arrows of C, and then that line in B computed is a free trivial observation. Okay, now prove that the degenerate images of atomic arrows in Bn are atomic in Bn+1. This is clear for atomic arrows in Bn that are also atomic in Cn. And now suppose that the degenerate image of some atomic arrow in Bn factors as G and F in Bn+1. But we know that C is a simplicial computad, so we have another factorization in Cn, and we have the following morphisms, and imply one of the phase maps that serves as a retraction of the degeneracy. Either G or F must map to an identity in Bn. So one of G prime or F prime is an identity one, but I suppose that it's not interesting proof, and but the result is important, because you think about the cellular cofibrant objects as just some simplicial computads, but simplicial computads is some algebraic object which can be formed by means of some comonad, and now we see that so consider the following 2 functions. You have a category of directed graphs and the category of small categories, and you have 2 adjoint functors f and u, and from this adjunction you can form a comonad which looks like this, and for any small category you have a comonad. So this resolution is a simplicial computed. This is some simplicial object, simplicial computed, and it is a cofibrant simplicial category by the lemma above. And so in the first step, this guy is just a free category. What are general arrows in this simplicial object? This arrow consists of the following data. You should form these arrows, and also with the this parenthesis, and so you have the following correspondence. If you have this guy, it corresponds to the following sequence of parentheses, and this construction corresponds to the situation when you compose and remove some parentheses, which are included into k times k times drawn parentheses. Okay, and in this situation, you just compose some inner parentheses. Okay. Now, so other examples show what is the correspondence between these expressions and some combinatorics of parentheses. Okay. So recall that the main task of this activity is to motivate the correct choice of an adjunction between simplicial sets and simplicial categories. And what is a naive way to construct the functor C? So you can just take say delta, and you can map it in a discrete simplicial category n. But in this case, the right adjoint will be an ordinary nerve, and it's not the case. So we should consider so-called coherent diagram, some shapes. So this guy is supposed to be a simplicial category that encodes a homotopy coherent diagram of shape n. And now I'm going to talk about homotopy commutative diagrams. So the definition of these objects: homotopy commutative diagram of shape A, where A is some small category, a map of reflexive directed graphs UA and UC that defines a functor from the category A to the homotopy category of C. And diagram F is a homotopy commutative if whenever we have the following equality in A, then FH and this composition lie in the same path component of the home space. Okay. And when C is locally can, this is the case when there exists one simplices such that we have an arrow in this direction and the arrow in opposite direction. Okay. So a homotopy coherent diagram of shape A is a simplicial functor. Simplicial functor between these simplicial categories or equivalently simplicial objects. So we can form the following map from UA to UC by means of the following functor and the map. So we start with UA and we map we apply U eta and we have in target this guy, and after that we apply the composite of U and this map, and now we have a homotopy commutative diagram. So okay, what is a homotopy coherent natural transformation? Homotopy coherent natural transformation is a homotopy coherent diagram of the shape A times 2, where 2 is, as usual, is just working arrow category, and homotopy coherent natural transformation is just a simplicial function between this view of this shape to the category C. So the main motivation is the following. Suppose that we have a commutative diagram F of the shape A. Is it possible to form a new diagram in which each object is replaced by a specified homotopy equivalent one? So we want to replace the objects by homotopy equivalent ones, and after that we want to have some diagram, and in the same way, in the case of natural transformations, if we have a natural transformation, is it possible to replace maps alpha n with the homotopic ones? The answer is no in general, but there is a result by Cordier and Porter given a homotopy coherent diagram in locally simplicial category and the family of homotopy equivalences. This data extends to a homotopy coherent diagram. So if our diagram is homotopy coherent, then we can do something like that, and there is no problem. Result transformations by Cordier and Porter. So consider the following example. Consider the category the following category, and we want to describe the home space. This home space, a few home space between objects 0 and 3 in this simplicial object. So what are of this home space? They are the paths of edges. So we should consider different paths consisting of arrows of this category. So for example, we can we start with this object, and after that we can apply L, and we will be in 3, or we can walk, for example, to the object 1, and after that we can apply K, and so on. So we have these possibilities. And these are just the vertices of this home space. What are the one simplices to obtain the one simplices? One should write one pair of parentheses for each for each expression in this line. So, for example, you can consider this composition, and we can put these parentheses in different ways, and these ways will produce different one simplices. But what is the case when these simplices are degenerate or non-degenerate? So the answer is quite simple, and it turns out that if your parentheses if there is a pair of parentheses which contains more than one symbol, then your simplex will be non-degenerate. So here we have a set of non-degenerate simplices, and of course this one are zero simplices, and these you can see are one simplices, and we have a two non-degenerate two simplices with these different positions of parentheses. So a question for you: what does this home space I wonder what does this look like? So this is some simplicial set, and what is it? What do you think? So we have four zero simplices, five one simplices and two simplices which are non-degenerate. So the answer is that this is just delta 1 cross delta 1. So in this case, so it looks like a cube, and it motivates the following definition, the desired definition of the functor C. So we put C of delta n as a homotopic coherent diagram of shape n, and the following lemma says that the category the category of simplicial categories admits all small colimits, and there exists a unique colimit preserving functor from simplicial sets to simplicial categories, which sends your n-simplex to some simplicial category or just by an appropriate left can extension, I suppose. So okay, and thus we have the desired functor. But there is a more convenient definition. Let J be a finite non-empty linearly ordered set, and I and G be elements of this set. Then we can form this PIG as a pose set consisting of the following subsets I in J, such that I contains I and J, and also contains all elements between any elements between I and J. So it looks like segments between I and J. Okay, and we can consider
using dumb combinatorial terms. It looks like the star of the simplex IJ.
Star of the simplex. Yeah. I mean that this guy looks like a segment, but of course, but the full space looks like a cube. This is a product of one-dimensional simplices in some. No, you're right, but I mean the nerve of this set is the product of one-dimensional simplices. Yeah, of course. So we can form the following composition law. If we have a I is less than J and the let is less or equal K in J, then we can form the following composition. If we have a subset I and I prime, then we can just form a union of I and I prime, and thus we will have an element in PIK. So the definition objects of this guy is just the elements of J and the home space is an empty set if I if j is less than I, and the nerve of the category of the pole set Pij if I is less or equal than j. And the composition is defined via the previous observation, with this construction. Okay, and some simple properties. The nerve of this I don't know, spine in some sense is just a cube, and also each simplicial set is contractible. This is because you can find initial objects in this category. So then the nerve will be, of course, a contractible space. And also there is a unique isomorphism if you take so the definition of pi and h are the same. So if you consider the homotopy, if you take a homotopy functor of this object, then you will have a n. And also by adjunction, this functor c. So by okay, by adjunction you can rewrite this isomorphism like this. Okay, and now discuss so-called null properties of C. C does not preserve products. The space are essentially never complexes or even quasi-categories. And now discuss the homotopy coherent nerve. Homotopy coherent nerve is right adjoint to this functor C. So if you have so the definition is follows. Is following one, and if C is an ordinary category, then the notion of homotopy coherent nerve is the same as ordinary nerve of your category. So you have the following isomorphism, where I recall that this means that this is a constant enrichment functor, C small. Okay, and the proof is quite simple. What are and simplices of this simplicial set? They are just they are described by this home, and you can apply the adjunction between functors C and pi, and use the fact that the previous fact, and then you can see this isomorphism. Okay, so an adjunction and Quillen equivalence. There is the following important the following theorem. The pair between already constructed functor C and the nerve coherent functor, this pair forms equivalence between Jayal model structure for quasi-categories and Bergner's model structure for simplicial categories. So the homotopy coherent nerve of a locally simplicial category is a quasi-category, and thus we have a some way to construct quasi-categories. But this way can be generalized for model categories. So you can consider your model category and take cofibrant objects and apply for this subcategory your nerve functor, and after that you will have some quasi-category. But we will discuss later. Okay, we have the following corollary. This is a Lurie's definition of weak equivalence in the Jayal model structure. The map of simplicial sets is a categorical equivalence if and only if the induced functor between the composition with the functor C and homotopy functor is an equivalence of H categories. Okay. So discuss some fruitful results on the junction. The first theorem is about that if A is any small category, then you have the following isomorphism. So if you apply your functor C to the nerve of some small category A, then it will be a simplicial object Fu of A. The next theorem says that if C is a locally simplicial set, then RC is a quasi-category. And the example which was mentioned earlier, for a simplicial model category M, we have a right William bifunctor, and we can form the subcategory consisting of cofibrant objects, and this category is locally can. After applying this coherence nerve functor, we will obtain a quasi-category, and also we have this isomorphism between the homotopic categories. So the original motivation by Boardman and Zwo, homotopy coherent diagrams and natural transformations assemble into quasi-categories, and this was an example that motivated the original motivation by Boardman and Vogt. So if you have a small category A, and you have any consimplicial category C, then you can form the following n-simplex or set of n-simplices, and the set of vertices is just homotopy coherent diagrams, and edges are homotopy coherent natural transformations between these diagrams. And by junction, you can think about these n-simplices just about this n-simplices in in this simplicial set. So recall that this RC is a quasi-category. And thus the exponential is quasi-category 2, and so we have a quasi-category which looks like this. Okay. Okay. So thank you for your attention. I suppose that I can end with this statement, these examples.
Okay, thank you so much for this nice talk and explaining to us this type of equivalence. I guess if you want, we can stop the recording now, or maybe.
Yes.
Okay.